You've worked with 4-bit units at this point, but you haven't been introduced to them as nibbles yet, unless you read that downloadable PDF resource from the first lesson. Our next lesson is going to dive into hexadecimal more thoroughly. You've only barely been introduced to that in this course. So before we do that, we want to understand this concept that makes hex work so elegantly, and that is the nibble. A nibble is 4 bits, half a byte. The name itself is like many things you'll find in computing programmer humor. At this point, it's from the 1950s and 60s for nibbles. If a byte sounds like bite that you eat, then half a byte must be a nibble. Just munching a little bit. But nibbles are the reason that hexadecimal exists as the preferred way to represent binary data in cybersecurity tools. Notice, as the preferred way, because we know that people started messing with hexadecimal long before the 1950s when we called it a nibble. Nibbles matter because 4 bits can represent exactly 16 different values. If we remember from our math, 1, 2, 4, 8, 16. If all 4 bits are off, 0, 0, 0, 0, that's 0. If all 4 bits are on, that's 15. Count them up. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 8, 9, 10, blah, 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 blah. Sorry, it's 9, 10, 11, 12, 13, 14, 15, 16 values from 0 to 15. Now, hexadecimal is base 16. It has exactly 16 digits, 0 through 9, then A through F. So you're often going to see hex in pairs of 2 as part of a hex number, because one hex digit represents exactly 1 nibble. So when we're grouping 2 together, we're getting the full byte. And that's all by design. So we want to think about the nibble 1010. In a decimal, that's 10. In hexadecimal, 10 is represented by the letter A. So the nibble 1010 equates to A in hex. We've got 1111. For the nibble 1111, that's 15 in decimal, which is F in hexadecimal. So 1111, that nibble equals F in hex. So it's actually powerful when you think a byte is 8 bits, which is exactly 2 nibbles, and that any byte can be represented by exactly 2 hexadecimal digits. So if we take the byte 10, 10, 11, 11, split it into 2 nibbles, the first nibble 10, 10 is A, and the second nibble 11, 11 is F. Put them together, you've got AF, 8 binary digits compressed into 2 hex characters. Simplification going on. So every cybersecurity tool that displays raw data typically uses hexadecimal. They're usually doing a conversion in the tool. When you open a file in a hex editor, you see a pair or pairs of hex digits. Each pair is 1 byte. Each individual hex digit is 1 nibble. When you see a MAC address like 00:1A:2B:3C:4D:5E, each pair of characters represents that 1 byte, 2 nibbles. 6 pairs means 6 bytes or 48 bits total. When you examine file signatures to identify file types, you're looking at hex values. The signature 4D5A that identifies Windows executables is 2 bytes, 4 nibbles, displayed as 4 hex characters. Understanding that 1 hex digit equals 1 nibble equals 4 bits is the key insight that makes reading hexadecimal intuitive. You're not doing complex math. You're simply knowing 16 mappings. The 16 ways to arrange 4 bits and their corresponding hex digits. In the next lesson is where we'll go more in depth into hexadecimal, but wanted to give you this little bridge as a prep to understand why it works so cleanly. The nibble is your bridge. 4 bits map perfectly to 1 hex digit, and that relationship is what makes hexadecimal the preferred shorthand for binary data throughout cybersecurity.